Kia ora tātou, ko tīmata te maangwa, ko tukituki te awa, no ahuriri ahua, ko udiavar toku whanua, ko Vikram toku inoa. Good morning. Today I will be talking to you about my research on modeling a space commodities exchange. Before we start, let's go through a brief journey of what most satellites go through during their lifetimes. Keeping it simple, because since there's a lot of nuances here, the owner comes up with an idea, goes to a satellite manufacturer that makes the satellite, goes to a launcher that launches the satellite, an operator takes care of the satellite, and then eventually the satellite is disposed of. The satellite market has grown, with 2020 having the largest number of satellites launched in a year since humans put objects into space. The space launch market has also been increasing and heading towards 1960s levels, with a projection by the FAA of 42.3 launches per year on average. The small satellite market has also been increasing, with a projection of up to 2,400 in the next 5 years, with currently 62% of them providing commercial services humans rely upon. There are a few problems associated with this increase, most notably crowded orbits, which started this research. But the one issue we're focused on today is the registration delays. Delays have been increasing, with the latest data showing a 2-year delay in a registration. There is also data inconsistency among countries' databases and the United Nations. Adherence has declined to a 70% worst case over the past decade. This presentation is an attempt at a solution to solving this problem, using the registration convention as a tool to help us with it, by voluntarily incentivizing actors in the space ecosystem to aid with managing the equilibrium of crowded orbits. Again, to start this, we must question whether spacecraft identity can be treated as an asset we can create financial liquidity to incentivize actors to behave appropriately in an area that can be legally classified as a common pool resource. There are 3 broad superclasses of assets: capital assets like stocks and land, consumables or transferable assets like air, water, wheat, etc., and finally store of value assets like gold. So which class would a spacecraft's identity fall into? Treating spacecraft identity as a crypto asset, an asset that is morphable into multiple super asset classes, providing the flexibility to create a digital political economy around space sustainability. It ensures all actors in the digital political economy have agency to govern, to regulate, to study and research, and do commerce, all at the same time. We start this by creating a space commodities exchange, by tokenizing spacecraft identity using cryptographic tokens in a crypto-economic system. There is historical precedent for this approach. The relationship between exploration, shipping, and finance is practically as old as finance itself. Merchants in medieval Venice and Genoa faced an ongoing issue: the high costs of financing their voyages to other parts of the world. The answer: the Commenda contract. The Commenda was a contract between a financier and a merchant to fund a ship's voyage to various ports so that a merchant could sell their goods. These contracts were revolutionary for their time due to a few reasons. They offered a passive investment approach. They offered a partial or fractional investment. It was a newly developed system for sharing profits and liabilities. Similar financing structures existed in the 19th century whaling industry as well. Let's go into some primitives before we dive in. Crypto-economic systems are data-driven, multi-scale, adaptive, and dynamic networks with a system-level state available to all agents. They use cryptographic tokens as information carriers, allowing for economic activities to emerge on top of shared infrastructure such as a blockchain. The best current example of this is the Bitcoin blockchain. In crypto-economic networks, the behavior at system level emerges from the behavior at agent level based on actions and reactions to rules and incentives set by policy design. And as such, we can design purpose-driven economic systems at the boundary of behavioral economics and dynamic decentralized coordination that bridges with platform economics. A bonding curve is a mathematical model for a cryptographic token that defines the relationship between that token's price and its supply. To bond into the curve implies buying the token, and to burn implies selling the token. They can be of different shapes and sizes, and they serve as automated market makers to create financial liquidity. And finally, a brief primer on fungibility, non-fungibility, and fractions. In economics, a good or an asset is considered fungible if that good or an asset's individual units are exchangeable and each of the parts that make it up are the same, of equal value and indistinguishable from each other. An example is cash. A non-fungible good or an asset is considered unique and generally irreplaceable. Its constituent parts that make it up are not necessarily equal and is normally not considered or valued. Example, a piece of art, or vintage car, or satellite's identity. Fractionalization is the process of dividing a good or an asset into subsequent parts, where each part is fungible. For example, taking a piece of art or real estate, which is non-fungible, and creating fractions of it that can be bought, sold, or traded like a fungible good or asset. So now that I have briefly described some of the crypto economics primitives, I'll move into the methodology used. I use a markets, mechanisms, and token design method that starts with a vision statement and a modeling goal that breaks down from high-level macroeconomic abstractions to microeconomic ones, where the markets represent the macroeconomic layer, the mechanisms represent the meso-economic layer, and the token represents the microeconomic layer. The vision of the exchange is to tokenize spacecraft identity, to manufacture liquidity for space industry actors, to aid them in collective long-term space sustainability via voluntary incentivized transparency. The goal of this modeling exercise is to determine the ability to develop this manufactured liquidity by tokenizing spacecraft identity. Next, we move into market design. The market broadly consists of three action spaces, namely internal actions, where actors within the market interact, external actions, where actors within the market interact with exogenous factors, and finally data actions, where actors capture and store specific data at the agent level that show up in the market. This last action space can overlap with the prior two, but can also be isolated. The market design space for our problem is a typical interaction between a satellite ID owner and an interested party that wishes to buy a fraction of the right to ownership of the satellite ID inside the Space Commodities exchange. We move now further down to the mechanism design space. The Meso-economic space is where policy is set and is further divided based on the macroeconomic action spaces. For the purposes of this modeling, not all Meso-economic spaces will be needed, as the decision is defined by the modeling goal. So for the sake of time, I will just discuss the ones I will be diving into further. Under the internal action space, we have governance, behavior, and signal mechanism spaces. Under the external actions, we have dynamics and static mechanism design spaces in response to exogenous factors. And finally, under the data actions, we have recognition storage for parameters we either capture or store at the microeconomic level that emerge at the macroeconomic level. The behaviors mechanism space relates to behaviors happening within the exchange. For this modeling exercise, we have 4 behavioral mechanisms: tokenize, bond, burn, and providing liquidity. Tokenizing involves creating a non-fungible token that contains the current state of the spacecraft ID at the time of creation. Bond involves bonding to the bonding curve, burn involves selling out of the bonding curve, and finally, providing liquidity is providing the fractional tokens in liquidity pools to earn a portion of trading fees from that pair pool. We captured the bonding rate, burn rate, and total value locked in liquidity pools, all 3 mentioned under the behavior mechanism design space above. We store the parameters of the total value locked, both inside and outside the exchange in liquidity pools covered under the superset parameter in the previous slide. And then finally the invariant, which we'll discuss in later slides. Let's move down to the token design. So we are at the microeconomic perspective of our crypto economic system. At this level, a token represents a metric that is tied to the value captures in the network. we'll go through three aspects of the token design space: the architecture, the value capture or tokenomics, and the bonding curve. To understand the architecture, I will discuss this via the Rocinante use case based on the popular sci-fi series The Expanse. Let us assume Jim is the owner of the Rocinante and is interested in raising financing for a mission to Ganymede from Earth, commissioned by the United Nations. The Rocinante is registered with the UN as part of the Registration Convention and is given permission to raise capital using its UN Commission International Designated ID. So he starts by tokenizing the Rocinante ID, creating a Rossi token, a unique privacy-preserving refungible token that represents the current state of the Rocinante, which could include carry capacity, mission profile, etc. Amos hears the news and decides to help Jim out and buys a few fractions of the Rossi token, or F-Rossi token, on a liquidity bootstrapping pool in a private sale since he's part of the Rossi crew. The collateral from the bootstrapping event goes into a multi-signature vault that Jim owns. Now Amos can choose to hold them, but instead uses a bot service to trade them in the open market by taking any arbitrage opportunities available from buying it during the liquidity bootstrap event. While not shown here, there would be other mechanisms available to Amos to earn a yield as a form of passive income, such as providing liquidity in exchanges for others who want to buy or sell F-Rossi tokens. Where can Amos capture value for his tokens? He can buy and sell them on other exchanges and provide liquidity for F-Rossi tokens on other exchanges. Other mechanisms can be explored, such as staking, voting on proposals to govern spending of the token's treasury. Imagination is kind of the limiting factor here from a mechanism design perspective. From Jim's perspective, he can choose to keep it simple by taking all revenue and distributing the way he sees fit, or can democratize ownership of the F-Rossi token. We are going to assume Jim wants to eventually democratize ownership of the tokens, so he initially sets up the token revenue distribution as shown in the figure, in the hopes to democratize governance in the future. The following is a brief breakdown on the Rocinante's total reserve. The total reserve consists of a proportion of the Rossi and the team of 5 and a treasury to help set up a dynamic issuance policy in the future. The token is issued as a fungible token and the token supply is uncapped, with a dynamic issuance policy based on a conservation ratio. The bonded collateral is UND or United Nations dollars, and the traded asset is a fractional token. The mathematical function used is a polynomial function with a dynamic pricing structure. Here P represents the price of the token, S the circulating supply, M is the gradient, which is a function of kappa, the reserve and circulating supply balances, and kappa is a function of the invariant or the conservation ratio. Feel free to play around with the simulator in the link provided on the slide. The invariant or the conservation ratio is a function of the total reserve balance and the current market cap of the F-Rossi token. We use this ratio as our guide to develop a PID controller that targets a low ratio range between 0.1 and 0.3. This dynamic issuance policy with a low conservation ratio ensures pump and dump attacks are less profitable by the low initial price rise based on circulating supply. Finally, I will end here with an initial model of the dynamic issuance policy control system and its block diagram and a differential specification. The next steps involve simulating this dynamic issuance policy system among other research questions, including crowded orbits. So what are the implications for this kind of system? It's an attempt to create digital public infrastructure that seamlessly transacts value among space ecosystem actors over an economic protocol within seconds. This compounds into several other domains, from microfinancing of not just satellites but expensive subsystems to more liquid with lower premium insurance policies, space governance 3.0, O different abstractions, especially governance, minimized dispute resolutions. And finally, customized commons communities to solve grand challenges like crowded orbits, space debris, and lunar mining token economies. To conclude, we introduce the problem and background for modeling a space commodities exchange, from issues related to registration delays to crowded orbits, and how this could be potentially solved through voluntary incentivized transparency by tokenizing spacecraft IDs, such as the United Nations International Designation Numbers. We show that this is not a new concept, but has historical precedent, and we introduce some of the primitives of crypto economic systems that will ensure voluntary incentivized transparency in the space community. We go through the markets, mechanisms, and token design methodology for the Space Commodities Exchange with the Rocinante as a use case. We develop an architecture, mention the initial value captures of a fractional token representing the state of the Rocinante as a refungible token, and simulate a bonding curve associated with the fractional token. Finally, we mention the future direction and the implications for creating such a digital public economic infrastructure for a more sustainable space environment and community. Thank you.